Hi, great. Welcome back. I'm glad you had a little rest. We're going to look at applying some of our skills of drawing Lewis structures just to include some of those polyatomic ions from last chapter. We're working with a polyatomic ion chart, remembering that those are groups of atoms acting as a unit carrying a charge. Those were on our polyatomic ion chart from last chapter. Groups of atoms acting as a unit carrying a charge. And I just want to kind of give a prospect of how to go about tackling those with these following examples. There, I'm catching up my definition. There we go. Groups of atoms acting as a unit that carry a charge. You can find each of these on your polyatomic ion chart provided to you as a test-taking tool from Chapter 3. For example, cyanide. Cyanide is a polyatomic ion. It has a carbon covalently bonded to a nitrogen, carrying a -1 charge. Notice that the -1 means that it has one extra electron. And so when carbon, who has 4 valence electrons living in group 4A, nitrogen, who has 5 valence electrons living in group 5A, and then notice that the -1 charge means that you have an extra electron, you get to add an extra electron to this dot structure that you create. So cyanide is going to be built with 10 dots, 10 valence electrons. Of course, we would know that the carbon and the nitrogen bond together. And so there's using the first two. We would see 1, 2, 3, 4, 5, 6. And then if I used 7, 8, there would be no dots left. But clearly I see that I have some work left to do, because I know carbon has a 4 bond requirement, nitrogen 3 bonds and 1 set of dots, and clearly that's not this structure. And so when I bring in the nitrogen's electrons, I still have carbon with 2 dots, leading to a triple bond, leading to the nitrogen. And then since this is an extra electron, what you'll always see is this is going to be placed in a bracket and the charge outside. This is a polyatomic ion. Now I know what you're saying. Hey, I thought that cyanide had a 4 bond requirement, and it certainly does, the carbon. But remember, it's an ion, and ions have first names. So perhaps we have it attached to a hydrogen cyanide. Or perhaps we have it attached to, some other element. You could see then that it creates a site of attachment for what it's looking for to create an electrically neutral compound. So the cyanide itself is looking to complete its carbon requirement. That's why it's an ion and not a molecule. Phosphate, PO4, 3-. That tells us phosphorus, who lives in group 5A, oxygen, who lives in group 6A, and we have a -3 charge, telling us that we get 3 extra electrons when building. So that becomes 8, that's doing math, that's 26 electrons by the time I'm drawing phosphate. So phosphorus, reaching out to each of those oxygens, that used 2, 4, 6, 8. 16 electrons left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I didn't add that right. Oh, here's my mistake. There's 4 oxygens. Linda. All right, so thank you. I'm just working out and I ran out of oxygens. Would it be all right with you if I just retallied quickly? Because when there's 4 O's and not 3, we get all kinds of different numbers. Oh my. Thank you for your patience. 3 extra electrons. Now I actually have enough dots to build the structure I'm trying to. This actually gives me 8. This is 32 valence electrons when added correctly. And we used 4 bonds, so that used 8, leaving us actually enough dots to complete each of the oxygen's octet. 3 sets of dots is 6 electrons, right? So then we had enough to complete the octet. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24 dots, leaving us 0. Then what you'll see is in a bracket and the charge outside, that's the polyatomic ion phosphate. Ammonium has a +1 charge. So what that means is that nitrogen, who's contributing 5, hydrogen, who's contributing 1, and it had a +1 charge, meaning it lost an electron. So I actually have to subtract an electron from my total. So 9 minus 1 is 8 dots available, which is perfect. We'll have nitrogen connected to all 4 hydrogen, and because it's a polyatomic ion, you'll see that positive charge outside. Hydronium, H3O plus, oxygen with 3 hydrogens, 1 set of dots, and a positive charge. Hydronium, H3O plus. Now, notice that when you have positive and negative ions, sometimes what you're seeing is that you don't follow that predicted pattern. Phosphorus. This is the pattern I would predict being in group 5. It's not following that, and that's why it has extra charges. Nitrogen, I would predict 2 sets of, or 3 bonds and 2 dots, and the bonds are not following that. That's why you see a charge on it. Oxygen, I would predict 2 dots and 2 sets of bonds, but it's not following that in the ion, and that's why it's carrying a charge. Polyatomic ions are kind of unique in the sense that we add or subtract electrons based on the charge, but then don't be mad when we don't follow the exact rules, because their ions are looking to change their bonds by attaching to something else. When we consider resonance structures, these resonance structures are 2 equally valid Lewis dot structures that have the same arrangement of atoms, but a different arrangement of electrons. Same arrangement of atoms. The atoms are connected in the same way. But the different arrangement of electrons. So the bonds between atoms may be different. Let's give you an example of one. Here is a polyatomic ion called the bicarbonate ion, hydrogen carbonate or bicarbonate. Now remember, because it's an ion, we may see that some of these bond rules are not being followed, and that's why it's carrying a charge. So here I have kind of carbon attached to all of those atoms there, and I know that I've got to do single bonds. I have, let's see, hydrogen who's going to contribute 1, oxygen will contribute 6. There's 3 oxygens there all together, and a carbon. So here we have, oh, and don't forget the -1 means you get 1 extra electron. So the -1 charge means we get to add an extra electron. So that's 18, 19, 24 dots. And when we did this, we did 1, 2, 3, 4, 5, 6, 7, 8. That leaves us 6 dots remaining. Golly, 1, 2, 3, 4, 5, 6. Oh, that's too many dots there, huh? How about... All right, so we're drawing this bicarbonate polyatomic ion, HCO3 negative. I've placed single bonds between all the atoms and tallied up that used 8, leaving us 16 dots. and I'm just going to place the 2 dot requirement around each. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Leaving me 4 dots remaining, and that's 4 dots to kind of make sure that I get a double bond to one of these oxygens and maybe another set of lone pairs to the other. And that creates the -1 charge on the oxygen. Now let me repeat why I didn't put double bonds here. And I'm just going to draw something wrong and then tell you why it's wrong. A moment ago I said I had 2 sets of dots, and I had this already staring at me, and I put 1 bond here leading up to this oxygen. Well, why didn't I just put a bond here instead of another set of dots? And what I want you to examine is what that did to the carbon. That's a rule breaker right there. See how too many bonds on the carbon? And so that's not allowed. Carbon will never, ever have more than 4 bonds, and I just gave it 5 bonds there. So that's not going to happen. So what I just did is give oxygen a set of dots and made it a -1 charge. I put a set of double bonds up and a single bond to make sure that I had 4 bonds only on the carbon, knowing that when I have a -1 charge, like we do on this polyatomic ion, the oxygen may be upset with its 2 bond, 2 dots requirement. It's okay, but carbon will never have more than 4 bonds. But you know, an equally valid choice? Equally valid in the sense that I could have placed the double bond leading out to the oxygen from the far right and a single bond leading up to this oxygen, and put the -1 charge up on the oxygen up high. These are 2 valid structures for this polyatomic ion called bicarbonate. I did a resonance structure. We will separate resonance structures with a double-headed arrow, saying one possible correct structure for this bicarbonate is to place a double bond to the oxygen going up and a single bond left or right. But another lovely choice is that I could have placed the double bond going to the oxygen to the right and the single bond up. 2 equally valid structures are called 2 resonance structures, where I'm given a choice of where to place the double bond between 2 equal choices. Now you notice the atoms are connected in the same order. H, then O, then C double bond O, C single bond O. They're same connectivity, but I'm just moving the location of the double bond and moving a set of lone pair electrons. I'm allowed to move electrons. I'm not allowed to move atoms. So which one is correct? Well, the answer is actually both of them are correct. When I had a carbon double bonded to oxygen, single bonded in this direction, and I said that this is a perfectly valid choice, and that this is an equally valid choice, where the HOC leads up to the single bond, and then this over here has the double bond. They're equally valid choices, 2 resonance structures. I want you to think of the true bond as being a hybrid of both structures, that these electrons are actually delocalized and spread apart evenly between all atoms involved in the bond. So if I were to redraw and give you a better picture of what's happening, the bond between the 2 oxygens is not really a true double, not really a true single bond, but it's delocalized, spending time evenly between the oxygen up high and the oxygen to the right. Do you see what I'm trying to draw there? Let me just clean it up and try to emphasize. From carbon to both oxygens have a delocalized double bond, and I'm going to draw dashed lines to let you know that it's not really a double bond in this direction single. It's not really a single and then a double in this direction, but that shared pair of electrons is being spread evenly, spread out, delocalized across multiple atoms of the same size. So it's got a larger region of space that it's spending time with. That the true shared pair are going equally between the up top and the to the right oxygen at the same time. A delocalized electron set. This actually is a very stabilized occurrence. The molecule gains a great bit of stability by being able to delocalize its electron pairs. So neither structure is actually true, but more of a hybrid of both structures. It's just, think about blending two structures. Did you know that a nectarine is a mix of a peach and a pear? I don't know if that's true. But it's not like a hybrid fruit spends time being one fruit and then the other. If a nectarine is a blend of a peach and a pear, it is not. I don't know what I'm saying. But a hybrid fruit like a nectarine doesn't go back and forth to being a peach and then a pear and then a peach and then a pear. It's a blend of the two structures, a hybrid. That's exactly what this molecule is. It's both pictures at the same time. When you mix red and blue, when you mix blue and yellow, what do you get? Is that green? It's not that green is a hybrid, or it's sometimes blue and sometimes yellow, but it's a hybrid of both. That's what a resonance structure is. So as we're considering delocalizing a double bond, remember, we're allowed to move electrons, but not atoms. So if we examine this structure, the carbon leading out to the hydrogens, leading out to a carbon double bonded to an oxygen, bring your eyes to this section of the molecule first. Carbon has two valid choices of where to place the double bond. It could place the double bond leading to the up top oxygen, or an equally valid choice is placing it to the right and making that the double bond. Oops, that's 3 dots. These two are known as resonance structures. We've delocalized the double bond. It spends time equally between both oxygens on that carbon. Examine letter B. Notice if you bring your eyes to where you see the double bond, because resonance will always involve a double bond. We cannot form a double bond on hydrogen, but we can form a resonance structure with the nitrogen next door. We would have hydrogen attached to carbon, and then instead of a double bond going up to the oxygen, we would place a single bond. And then the double bond could be delocalized between the nitrogen and the carbon. So another valid resonance structure is to distribute the double bond in the opposite direction from the carbon. Knowing that a resonance structure actually is a hybrid of both, that the oxygen carbon bond and the nitrogen carbon bond truly have a delocalized electron pair being shared between both atoms. And we represent that in two resonance structures separated by a double-headed arrow. Those are resonance structures of our compound. A very stabilizing effect. Label each pair of compounds as resonance structures or not resonance structures. Remember the two rules here. You're allowed to move electrons, which are bonds. You're allowed to move bonds in electrons, but not allowed to move atoms. So one of the first things to note is, do the atoms, are they attached in the same way? I have a nitrogen, carbon, oxygen. Nitrogen, carbon, oxygen. Perfect. I'm not breaking the atom rule. Then I'm just checking to see if those two are resonance structures. All I've done is moved a set of electrons, and that's clearly what's happened. This set of electrons became a bond, and that's separated. So yes, these are resonance. The letter B, this looks funny to me. Notice here the oxygen is part of a structure in the bone, it's attached between the two carbons. And now all of a sudden the oxygen has moved a completely different location. So this is not a resonance structure. You cannot move atoms, only bonds and electrons. I see that happening down in this example as well. The carbon and the nitrogen have exchanged places. I can't do that and have a resonance structure. I'm not allowed to move atoms. So these are not resonance structures. Let's see here. Carbon, carbon, NH, carbon, carbon, NH. This has the same atoms, right? Same connectivity. So therefore, all I did was move electrons. That's certainly the case. It looks like a set of electrons went to make a double bond. The double bond became a set of dots, and that's what separates these, are moving electrons. Same connectivity, different sets of attachments of bonds. So yeah, this is a resonance structure separated by a double-headed arrow. Let's draw 3 resonance structures for the polyatomic ion called carbonate. Remember carbonate from last chapter? CO3 carrying a 2 negative charge. That means we get 2 extra electrons. Carbon has 4 valence electrons, lives in group 4A. Oxygen with its 6 valence electrons. And then the negative 2 charge says, hey, we get 2 more electrons to contribute to our structure. That's 24 total dots. Carbon in the center, attach back all 3 oxygens and retally. 1, 2, 3, 4, 5, 6. That's 18 more dots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 13, 14, 15, 16, 17, 18 dots. We're done. Except carbon doesn't have the 4 bonds it needs. So we need a multiple bond to satisfy the carbon. We need a double bond. So what do? Do we take it from this oxygen? Do we take it from this oxygen? And do we take it from this oxygen? And the answer is absolutely yes. That's our 3 structures. Do you notice that we have 3 equal choices to create a double bond? Choice number 1, let's put a double bond between the carbon that's lying to the left I know that it's upsetting the oxygen's 2 bond, 2 dots, but that's why it's carrying a charge. It's got 2 oxygens that are upset, but that's 1 equal valid choice for an ion carrying a charge. When it's charged, it's going to break its normal oxygen rule where we want 2 bonds, 2 sets of dots. The negative 2 charge says there's 2 oxygens in there not performing that way. But why did I go there when I could have equally drawn a structure in this direction, single bonds to either side? That's another very valid choice. That's a second resonance structure. And do you see the next choice? Oh yeah, The carbon double bond could have been leading out to the right, and all of those dots up here and over here, creating a third equal resonance structure. Now remember, it's a hybrid. It's not really any of them. It's a hybrid of all of them at the same time. That when I stand at the carbon and I look out at all oxygens, they're all equal distance away because I have 3 oxygens that are delocalizing an electron pair. Delocalized means it's not really spending time only between the carbon and oxygen to the left. It's not really just spending time between the carbon and the oxygen on top, or the carbon to the oxygen to the right, but it's spending time equally in all directions. Delocalized bond sharing. That's what resonance is all about. A delocalized sharing of electron pairs. With carbonate, we had 3 equal choices because the oxygens in all 3 directions provided 3 choices of where to go. You've now got a little bit of reading to do, an assigned reading section on section 4.3b, focus on the environment. You can read a little bit about ozone and select out 3 to 4 most important points to complete that part of your note pack. But while I have you here, I'm going to keep going onto the page 7, and let's just do a quick lesson on naming covalent compounds. You're going to find this so easy. To name a covalent compound, remember there's no such thing as charges. And so all of those ionic compounds we practiced last chapter, they have their own set of rules because they have, metal to nonmetal, charges, crisscross, create electrically neutral compounds. None of that plays a role because we're sharing electrons. So here's the set of rules. To name them, you simply name the first element as appears on the periodic table. You'll name the second element ending it with "ide." That's just like the binary ionic compounds. Binary molecular compounds will also end in "ide." We'll use a prefix to indicate the quantity of each. Do you hear a mono, a di, a tri, and so forth? Using the prefix to tell us how many of each element are present. Now, a couple of little side notes. Mono is the prefix for 1. If you see the first element has a subscript of 1, you may choose to leave it off. For example, CO2. We do not have to say monocarbon dioxide. If it's in the first position, you can choose to leave it off, carbon dioxide. But if it's in the second position, you must put the mono on, carbon monoxide. It is not okay to leave the mono off of the second. So mono must be used in the second position. But if it's in the first position, mono is left off. But all other prefixes have to be there. The other thing you'll notice is that if you have 2 vowels playing a role, 2 vowel sounds, it tends to trip you up. And I just gave an example. Mono, and then if I had the oxide, it would sound like monoxide if I left both vowels together. For this molecule, monoxide. So lop off the first vowel and just say monoxide. It just is easier to read. Alrighty. So let's practice a little bit using that. And I guess what we should really do before we name them is become familiar with what are those prefixes we're going to hear in the names. And those prefixes we should fill in together. And I'm going to just create a little chart down here. If I hear the number 1, I want you to name that with the prefix mono. If you see a subscript with prefix di, that represents the number 2. Tri represents 3. Then we hear tetra for number 4. For number 5. Then we hear hexa for number 6. We then hear hepta for number 7, octa for number 8, nona for number 9, and deca for number 10. When I'm looking at prefixes, mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca, know those by heart so that you can name binary molecular compounds using prefixes to represent how many of each atom you see. And it gave us an example there. Let's dive in and try. It says NO2. How would we name the molecule NO2? Well, rule number 1 says, say the name of the first element just as it is. It has a prefix of mono to represent the 1 that's not written but we know is there. But we're going to let mono go in the first position. The next element is oxygen. We change the ending to "ide," so it becomes oxide. And I'm going to let you know there's 2 of them there. Dioxide. Nitrogen dioxide. Now, a moment ago I said if 2 vowels are present next to each other, omit the first vowel. Doxide doesn't work that way. You're going to let them if it's 2 of the same vowel, right? So di is going to be kept. Dioxide, and eventually, just like any new language, it just becomes clear as it sounds correct. Dioxide is 2 vowels together, but it's not forcing your tongue to trip. N2O4. Say the name of the first element just as it appears, but place the prefix in front of it to let you know that there's 2 of them. Dinitrogen. That's N2. Dinitrogen. Now all of a sudden I have 4 oxygens. So that's tetraoxide. I'm going to write that and then we can decide. Tetraoxide has a double vowel. Tetraoxide. In this case, tetroxide actually is less of a tongue trip. Tetroxide. It doesn't matter to me if you're typing them in tetroxide or tetraoxide. It will eventually get to where you know what sounds correct. Tetraoxide. What if you hear the formula from a name? Silicon tetrafluoride, diphosphorus pentoxide. Here's an example where we lopped off a vowel just to make it sound better. Pentaoxide. We got rid of the A and just went straight to the O. Pentoxide. Less of a tongue twist. Silicon, no prefix, so I know it's just 1 atom of silicon. The element fluoride tells me that it's F, the elemental symbol F, and the prefix 4. SiF4, silicon tetrafluoride. Here's a prefix 2 for di element of phosphorus, P2. Pentoxide tells me I have 5 oxygens. So much easier than ionic compounds, aren't they? Silicon dioxide. Silicon, just 1 of them because I did not hear a prefix. Dioxide, notice there's 2 vowels there. I can't argue that, but it just sounds right. Dioxide, SiO2. Phosphorus, no prefix, so I know there's just 1. Then I see trichloride, Cl3. Phosphorus, trichloride. Sulfur, trioxide. Again, there's 2 vowels, but it just sounds better. Sulfur trioxide rolls off your tongue better. Dinitrogen trioxide. Dinitrogen trioxide. I'm going to take a couple important notes. No crisscross in molecular compounds. We did that with charges, so that's ionic only. That means the prefix you hear attaches directly to the name of the element. Trichloride, oh, 3 Cls. Trioxide, 3 oxygens. No such thing as crisscrossing. Other thing to emphasize, SO3, we just named a moment ago, sulfur trioxide. I want to compare that to this. Now all of a sudden I see 1 sulfur, 3 oxygens, but a -2 charge. Sulfur trioxide is a neutral molecule. There's no charge there, so we simply say the name of the first element, say the name of the last element, and an "ide," and use prefixes. This is a polyatomic ion, a group of atoms acting as a unit carrying a charge. This is not a molecule. They are not the same thing at all. SO3 2 negative, we use our polyatomic ion chart to name that. And we would see that this is called the sulfite ion. SO4 2 negative, oh, that's the sulfate polyatomic ion. SO4, no charge, is a neutral molecule. So that's where we would hear sulfur tetraoxide. Just wanted to emphasize. You should practice. Pause the video. You've got a great opportunity to practice binary molecular compounds and nomenclature. Come back to the video when you're ready to start up again. Pause, practice, come back. All right, you ready to check? You've spent time with your periodic table. If you're cheating yourself of the practice, it will take you longer and longer to become proficient. The learning deepens when you practice yourself and then come back to check. That's me just giving the imploring you to do your work. Letter A, phosphorus tribromide. Letter B, sulfur trioxide. Letter C, nitrogen trichloride. Letter D, diphosphorus pentasulfide. Letter A, sulfur hexafluoride. UOR, fluoride. Letter B, carbon tetrabromide. Letter C, dinitrogen monoxide. Did you remember the mono? Lop off the double vowel, monoxide. Letter D, tetraphosphorus decaoxide. Decoxide. Decaoxide. I'm going to lop off that vowel and just get decoxide. Alrighty, how'd we do? Selenium dioxide. Carbon tetrachloride. Dinitrogen pentoxide. Silicon tetrafluoride. Nitrogen monoxide. Phosphorus triiodide. There's a double vowel. It sounds better. Triiodide. Triiodide. The iodine is part of the word of the element. Triiodide. As a matter of fact, there's 3 vowels in that word. It just takes practice to remember what sounds best. Triiodide, Pi3. Oh, you're doing such good work. Let's pause our video. We're going to come back and talk about what it looks like to be in a molecular shape in terms of the VSPER theory. So good work so far. We're just going to take a little break, come back when ready to look at the VSPER chart.